Okay, so I told you guys yesterday, what we are learning today is how to solve a homogeneous linear differential equation. So we've looked at before, here's the solution, verify that it's a solution. We're going to talk about today how to find the solution. We are only going to do homogeneous. We're not going to get to the non-homogeneous. We are going to start by returning to example number 2 from 8.1. In that example, we saw the following differential equation, or the following system. dx dt is equal to x add 3y. dy dt is equal to 5x add 3y. And then we talked about another way to write this is x prime is equal to 1, 3, 5, 3x. And we talked about x is the vector xy. Okay, so then with that system, we saw that the system had two solutions, and they were the following. x1 is 1, negative 1 e to the negative 2t. And we saw that x2 was 3, 5 e to the 6t. Okay, so what we notice is that both solution vectors have the same form. Okay, the form that they have is x is equal to k1, k2, e to the lambda t. I is 1 and 2 here for the two solutions. So the question is that the way the solution is always going to look? Is the solution always going to be in that form? So we're going to investigate that a little bit and then do a few examples. So let's consider just a general homogeneous system. So x prime is equal to ax. Okay, so above we said that x was k1, k2. I'm just going to write that as k. E to the lambda t. I'm going to replace x with this. So I get a times k e to the lambda t. If I were to take the derivative with respect to t, that would bring down a lambda. So I'm going to replace that for x prime. So x prime will be k lambda e to the lambda t. So all I did is replace x and x prime. Okay. Now that e to the lambda t we can divide out of both sides. Remember, we can only do that because this term will never be 0. So you don't just get to like willy-nilly divide by whatever you want to. We get to divide those out because it will never be 0. So then we have lambda k is equal to a k. Now remember, lambda is a constant. A is a matrix. That's very important. Okay, what we can do is move this to the other side and factor out the k. So we're going to have everything equal to 0. We factor out a k. We're going to have a minus. Do you remember talking about how you can't do a minus lambda? A is a matrix, lambda is a constant. So instead we did a minus lambda I. This should look familiar. Does it? Okay, so then we talked about this has two solutions. One solution it has is that k equals 0. That's a trivial solution though, so we don't care about that one. So we're going to say that k does not equal 0 because we don't want the trivial solution. Instead, what we want is for the determinant of a minus lambda I to be equal to 0. So we want that matrix to be non-invertible. If it were invertible, you'd be able to multiply by the inverse, move it over to the other side, and you would get k equals 0. So if this matrix is not invertible, you won't get k equals 0. With me so far? Okay, so here's what we learned from that. We learned that x equals k e to the lambda t will be a solution of our system x prime is equal to ax, if and only if lambda is an eigenvalue of A, and K, this should make sense, is an eigenvector corresponding to lambda. So you should have maybe been able to see that because I told you we would be using eigenvalues and eigenvectors for these notes. Okay, so we got a quick theorem to write down, and then we'll jump into some examples. Our theorem, let lambda 1, lambda 2, all the way to lambda n be distinct real eigenvalues of the coefficient matrix A in the equation x prime is equal to ax. Let k1 all the way to kn be the corresponding eigenvectors then the general solution is the following. So we're using the superposition principle. We get x is equal to c1 k1 e to the lambda 1t plus all the way to cn kn e to the lambda n t. First example. Okay, I have two examples. I have a 2 by 2 matrix and a 3 by 3 matrix. The 3 by 3 is just an extra step. Are we okay if we just stick with the 2 by 2 so that we can get through this? Okay, here's what we are solving. dx dt is equal to 1/2 x add 9y. dy dt is equal to 1/2 x add 2y. Okay, so here's how you're going to start. First thing that you're going to do is you're going to put this in matrix form. So we get x prime is equal to, our coefficients are 1/2, 9, 1/2, and 2 times x. That tells us what matrix A is, our coefficient matrix. Okay, next thing you're going to do is you're going to have to find the eigenvalues. Eigenvalues are when the determinant of A minus lambda I is equal to 0. So I have to subtract lambda from the diagonals. So I get 1/2 minus lambda, 9, 1/2, and 2 minus lambda. And I want that to be equal to 0. Okay, so when I do that, I get 1/2 minus lambda times 2 minus lambda minus 9/2. You're going to multiply that out, combine like terms. Are you okay if I tell you what it ends up being? Mm-hmm. Ends up being lambda squared minus 5/2 lambda minus 7/2. We want this to be equal to 0. It's quadratic, so you can do the quadratic formula or you can factor it. I will tell you this ends up being lambda minus 7/2 and lambda add 1. So we get two eigenvalues here. The first one is -1, the second one is 7/2. Okay, this is one possible case. So I told you there's three cases we're going to look at. You can have two eigenvalues that are different. What else could happen? They're the same. They're repeated. Imaginary. So those are the three that we're going to do today. This is a case where they're both real and they're different. Next thing that you're going to do is you're going to consider those two eigenvalues separately. And for each one, you need to find the corresponding eigenvector. So in this case, if you remember, we do a minus 7/2i augmented with 0. So 7/2 you're just plugging in here. 1/2 minus 7/2 gives me -3. 2 minus 7/2 gives me -3/2. Okay. I'm going to do two things at once. First thing that I'm going to do is this top row, I'm going to divide by -3. If I do that, I get 1, -3, and I'm going to have a 0 and a 0. Okay. From here, I need to make this a 0. So what I'm going to do is I'm going to take row 1 and multiply by 1/6 and add it to row 2. Because in this case, I'll get -1/2. I can add to 1/2 and I get 0. Then I get 9/6, which is 3/2, add -3/2, and I get 0. Now, do you guys remember that this should happen? You should have zeros because you want your K1 in terms of K2? Okay. So now, what this tells us is that K1 minus 3K2 is equal to 0. So K1 then equals 3K2. This helps us find our first eigenvector, which is K1, but it's a vector. It's not the same as that K1. If I choose K2 to be 1, my K1 will be 3. Okay, next thing, or next eigenvalue is -1. So in this case, we're going to have a plus I augmented with 0. So we have 3/2, 9, 1/2, 3. Okay, first row, I'm going to multiply by 2/3. So I get a 1 here. And then I'll have 18/3, which is 6. Then I ultimately need this 1/2 to be a 0. So I'm going to take row 1 and multiply by -1/3 and add it to row 2. So then I get -1/2, add 1/2 is 0. -3, add 3 is 0. So K1 is equal to -6K2. So our second eigenvector then, if I choose K2 to be 1, I get K1 to be -6. Okay, and please recognize that you all might get different eigenvectors, but they're still going to be constant multiples of each other. So if you choose K2 to be -1, you'd have +6. Our solution then. Solution is going to be C1, the eigenvector, which is 3, 1, e to the 7/2 t, plus C2, the second eigenvector, which is -6, 1, e to the -t. That is one way to express the answer. Sometimes your answer will be expressed as a system. So the other way to express this would be x of t is equal to, and you just go across. So C1, well, 3 C1 e to the 7/2 t minus 6 C2 e to the -t. And y of t will be c1e to the 7/2 t, add c2e to the negative t. I believe on WebAssign you'll be using this top format. Okay, questions on that? Really, it's not a whole lot different. I have another example. Are you okay if we skip it and go to the next case? Yeah. Okay, next case that we're going to do is what happens if you have repeated eigenvalues. Okay, with repeated eigenvalues, two things are going to happen, or two things could happen. First, like subcase, for some n by n matrices, you may find m linearly independent eigenvectors, k1 through km, corresponding to lambda I of multiplicity m. Okay, so sometimes you're going to have an eigenvalue that has multiplicity m, and you will find m different eigenvectors. If that's the case, then your general solution will contain the following. So we don't know that this is the only eigenvalue. There could be other ones. It will contain c1, k1, e to the lambda I t plus c2, k2, e to the lambda I t all the way up to cm, km, e to the lambda I t. In addition to all the terms that come from the other eigenvalues. So we talked about before, if you have an eigenvalue of multiplicity 2, sometimes you're going to get two different eigenvectors, sometimes you won't. This is the next case. If there is only one eigenvector corresponding to lambda I of multiplicity m, then the m linearly independent solutions are the following. So if there's multiplicity m, you're going to have m solutions. It just depends on the eigenvectors will determine what they look like. So here you have m solutions. They're all different eigenvectors. Here you have one eigenvector. You still need to have m solutions, though. So here's what they're going to look like. You will have x1 is equal to k11 e to the lambda I t. This is an I, k1I. x2 will be k2I t e to the lambda I t plus, sorry, change it back to a 1. It's a 1. k22 e to the lambda I t. This will keep going all the way down to xm is equal to km t to the m minus 1 for m minus 1 factorial e to the lambda I t all the way up to kmm e to the lambda I t. Okay. We did one in class.
What was that you like scratched out there?
It's a 1.
That's
1, 1. Yep. There's a 1 there too. Okay. We did one in class, I believe, where there was an eigenvalue of multiplicity 2 that had 2 eigenvectors. Yes? Do you guys remember that from before?
Yeah.
Okay. Is that intuitive then, what the solution will look like? No. Okay. We're good with finding the eigenvalues, right? Mm-hmm. Or we could finding the eigenvectors. Mm-hmm. Okay. What we're going to do is I'm going to show you 2 examples. The first one, though, I'm going to give you all the information, and we're just going to write the solution. Sound good? Okay, I know I'm going through this quickly, but I feel like it's better if I'm here to show you than to teach you another way. Okay, second example. We are solving the following. X prime is the 3 by 3 matrix. 1, -2, 2, -2, 1, -2, 2, -2, 1. Okay, you all are comfortable finding eigenvalues and eigenvectors if I asked you to, yes? Okay. Here's what your eigenvalues are that you get. You get -1, -1, and 5. The -1 gives you 2 different eigenvectors. The first one it gives you is 1, 1, 0. The second one is 0, 1, 1. 5 gives you the eigenvector 1, -1, 1. So all we're going to do is write what the solution looks like. It's going to be exactly what we did in example 1. It's going to look exactly the same. X is equal to C1, K1, which is 1, 1, 0, e to the -t, plus C2, the second eigenvector, which is 0, 1, 1, e to the -t, plus C3, third eigenvector, e to the 5t. Okay. Good on that one? Yeah. Okay. The case that is definitely more interesting is when you have multiplicity m, but only one eigenvector. That one is going to be different. This one is not intuitive. So we're going to go through this one together. Our system is x prime is equal to the 2 by 2 matrix, 3, -18, 2, -9 times x. Okay, so first thing we're going to do is we're going to find the eigenvalues. So we're going to take the determinant of a minus lambda I, and we're going to set it equal to 0. In that case, it's 3 minus lambda, -18, 2, -9 minus lambda. So we have 3 minus lambda, -9 minus lambda, multiplying them, add 36 is equal to 0. Can I just get to what this ends up being? Okay. This ends up being lambda add 3 squared is equal to 0. So in this case, both of our eigenvalues are -3. Okay. So let's look at our eigenvalue and find the corresponding eigenvector or vectors. We're going to look at a, add 3i, and augment with 0. Okay. So 3, add 3 will be 6, -18, 2, add 3, we get -6. I'm going to divide the top row by 6, and I get 1, -3, 0. Then if I take negative 1/3 row 1, I can add it to row 2. So negative 2 add 2 is 0. 6 add negative 6 is 0. Okay, so we get k1 is equal to 3k2. So our first eigenvector, if I plug in a 1 for k2, I get a 3. Okay, a 2 by 2 matrix needs to have 2 solutions. This gives us only 1. So the solution that we get first is 3(1)e to the negative 3t. Okay, here's what the second solution is going to look like. The second solution will be of the form k2 is equal to k t e to the lambda 1t, add p e to the lambda 1t. Okay, so I'm going to point out a few things, what they are. This is k, negative 3 is the lambda. So this solution, we already know what it's going to be. It's going to be this k, t, that e. P is what we need to find. Okay, so here's how you find P. To find P, you are going to solve that a plus 3i P augmented with k, not with 0. Okay, so take this same matrix up here, this 6, negative 18, 2, negative 6. This time we augment with k. This is k, that 3, 1. Okay. I'm going to start out the same way I did before. Divide the top row by 6. So we get 1, negative 3, 1/2. And then if I take negative 1/3 times row 1 and add it to row 2, we did that above and we got 0, 0. In this case, we get negative 1 add 1 is 0. So this tells us that P1 minus 3P2 is equal to 1/2. If we go to find our P then, I'm going to make P2 0, which makes P1 1/2. Okay, with me so far? Sorry. Move us away from the sun a little bit. Okay, you guys good so far? Yeah? Okay, so what this tells us is that our second solution will be the 3(1)t e to the negative 3t plus this p, which is 1/2 0 e to the negative 3t. That is not the general solution, though. The general solution contains both of these solutions. So the general solution is our x1, so c1, 3(1)e to the negative 3t, plus c2 times the second solution, which is 3(1)e to the negative 3t, plus 1/2 0 e to the negative 3t. So x1, x2. Whew. How are we doing so far? We're doing great? Okay. For the complex eigenvalues, I was going to go through like deriving all of it, and I don't think we can do that in 13 minutes. So can I tell you the theorem and then we do an example? Yeah? Is this too much for us? Have I overloaded our brains?
Nope.
No, we're good?
Just put all the notes out.
Yes, but they are not easy to follow. Like I do things like that, and then like you have to find where I went. So they're not in order at all of what we did. Do you still want them? Okay. Great. I'll put them up there for you if you... It has everything that we've done, just in a different order. Okay. Last case is when you have complex eigenvalues. Let's consider the eigenvalue lambda 1 is equal to alpha plus I times beta. And this is an eigenvalue of x prime is equal to ax. And we're also going to define b1 is equal to 1/2 k1 plus k1 the conjugate this is the conjugate. Just write this down. We're going to do an example. Just write it down. We're going to do an example.
Wait, so is it a line under vector?
Yes. So it's k1, the bar to denote conjugate, but then it's also a vector. b2 is I over 2 times negative k1, add k1 conjugate vector. Guys, I know this looks bad. It's not going to be that bad. Okay? Then, you're going to have two solutions. Here's what they're going to look like. The first one is going to be b1 cosine of beta t minus b2 sine of beta t e to the alpha t. Second solution will be b2 cosine of beta t plus b1 sine of beta t e to the alpha t. And these are linearly independent solutions. Okay, that b1 and b2 are incredibly confusing. I understand that. Here's what you really need to know. When you find k1, b1 is the real parts of k1. b2 is the imaginary parts of k1. Okay, we're going to do an example that will make more sense. It's a combination, BB, beta, beta, BB, beta, beta.
So which ones are beta?
Anything in a cosine is a beta. Cosine and sine is beta. All the rest are just B's.
Why are the first ones not vectors?
Because I was too lazy to put the bars.
Oh.
Okay, can we do an example?
Yes.
So that I promise you, you look at this and you're like, I have no idea what it means. Like, we'll do an example. It's not that bad. Okay? Here's your example. X prime is equal to 6x minus y. Y prime is equal to 5x add 4y. Find our eigenvalues. We're going to do the determinant of a minus lambda I. So we have 6 minus lambda, negative 1, 5, and 4 minus lambda. I'm assuming you can find the determinant, yes?
Yes.
quadratic ends up being lambda squared, subtract 10 lambda, add 29 equals 0. Does not factor, so you're going to have to do the quadratic formula. When you do, you get lambda is 5 plus or minus 2i. Okay, here's the good news when you have complex conjugates, or when you have complex eigenvalues. You only need to find the eigenvector for one of them. And I'll show you why. Okay, well, I'm going to show you where to go from there. We're not going to go through the derivation. We are only going to look at the eigenvalue 5 plus 2i. We're going to find the eigenvector that corresponds. So we're going to do a minus lambda 1i augmented with 0. Okay, so 6 minus 5 plus 2i. 6 minus 5 is 1, and then we have minus 2i. Negative 1, 5. 4 minus 5 is negative 1 minus 2i. Okay. This one I'm going to do a tiny bit differently. I'm not going to be concerned about getting a 1 here. I don't really need a 1 here, so I'm going to leave the top row exactly how it looks. What I am going to do is I'm going to take 5 times the first row. I'm going to multiply the second row by 1 minus 2i, and then I'm going to subtract them. Now, that should make sense. All I did is flip these two and then subtract them. So you know that the first term is going to be 0. With me? Mm-hmm. Okay. If I multiply this one by 5, I'm going to get negative 5. If I multiply these two, you guys know how to multiply those two? Okay. You should intuitively know that you're going to get a 0. Okay. If we do it though, so 5 times negative 1, we get negative 5 minus 1 minus 2i, negative 1 minus 2i. Just to verify that we do in fact get 0, we get negative 5 minus 1 times negative 1 is negative 1. I get positive 2i, negative 2i, and then I get positive 4i squared. I squared is negative 1, so that's negative 4 plus 1 is negative 5. So I do in fact get 0. With me so far? Mm-hmm. Okay. So this top row then tells us that 1 minus 2i times k1 is equal to k2. Right? Because it was minus k2 and I just moved it over. Okay. So our first eigenvector then, if I put a 1 in for k1, my k2 will be 1 minus 2i. Okay. Ready to see where this goes? Mm-hmm. We're almost done. Almost done. Okay. So I'm just, wow, this is like really crooked. Okay. I'm going to write down that K1 one more time. That's all we need. We do not have to find the other eigenvector. What you're going to do is you're going to split that up into the real parts and into the imaginary parts. The real part is 1, 1. The imaginary part is 0, negative 2. The real part is b1. The imaginary part is b2. So then finally, our general solution, okay. Our two solutions are going to be in this form. I want the general solution though, so I'm going to have to write them together. Okay, so I'm going to have C1 times my first solution, which is B1 cosine of beta t. B1 is that 1, 1. So we get 1, 1 cosine. Our beta in this case is 2. Do you guys know where that comes from? Where does it come from? The eigenvalue, yes. Alpha plus beta I, What was ours? 5 plus 2i? So it's the 2. Okay, cosine of 2t minus b2, so minus b2 sine of beta t e, what's alpha? 5, the 5t. So if you remember, we had 5 plus 2i, that's our alpha, that's our beta, plus c2 times our second solution, which will be b2, so the 0, negative 2, cosine of 2t, plus b1, which is that 1, 1, sine of beta t e to the alpha t. Okay, so I would argue that solution looks the worst, but it's the easiest to find. Because you just have to find one eigenvector and then you're done. Okay, I know I threw so much at you, but do we get the gist?
Yeah.
Do we have enough information to be able to do the homework?